Okay, today we're going to start doing a study on nuclear reactions. So we know that if we have an element X, that element is defined by the X being the name, and the atomic number and the mass number, where the atomic number is the number of protons and the mass number is the protons plus the neutrons. For example, the element helium atom has 2 protons and it can have a mass number of 4, and that will tell us that there's going to be 4 minus 2 neutrons. Every element can be defined by its atomic number and its atomic symbol here. But the mass number can vary. So the mass number can vary from can vary from atom to atom. And that's because we can have different isotopes of the same element. So the same element, although it has to have the same number of protons, it can have different number of neutrons. And that variance in the number of neutrons leads to isotopes. If we look at the following, showing it's gone too high up. So this is this shows us the number of protons down here. It's just the number of protons is down here. And this is the number of neutrons. And what we can see here is the black dots represent isotopes that are stable, and on either side you have variant isotopes that are not stable, and the different colours are representative of the half-lives of these isotopes, with the kind of blue-white colour as the ones which are the least stable, and the darker the colour, the most stable. Let's get rid of that too. So in the nucleus, you've got, your nucleus is made up of protons and neutrons. And at the turn of the century, as we saw with our study of the Standard Model, our understanding of how the nucleus is made up was something that we were really gaining knowledge about and understanding about. Einstein was at the forefront of this investigation, and in 1905 he published a paper in which he launched his famous equation E equals mc squared. Now this elegant and very simple looking equation tells us that energy and mass are equivalent. So E is energy and m is mass, and c is like a kind of a constant of proportionality. It's the speed of light squared. But if you think about energy being proportional to the mass, and when we have something that's proportional, we need a constant of proportionality. The speed of light squared is that constant of proportionality. So this implies that for 1 kilogram of mass, you can produce 9 times 10 to the power of 16 joules of energy. If all that mass, all the energy in that mass was released, that's how much energy you would get. And once this understanding became known, the race was on to be able to unlock this energy potential within atoms, so that we could generate energy that would be beyond our wildest dreams. The unlocking of this is the key to unlocking our energy needs. It has also been the key to unlocking untold destruction in the form of the atomic bomb. Now, this, as people began to penetrate the inner workings of the nucleus, the power of this equation quickly began to be realised in a very real way. So, if you do a detailed investigation into the mass of nucleons, we find missing mass. When the mass of all the nucleons is combined and is measured in combination, the combined total was found to be less than the simple sum of the individual masses. So say you've got your nucleon, you've got your I'm going to get some different colours to show the different types of nucleons. So you've got your neutrons, and you've got your protons. If you add the mass of each neutron plus the mass of each proton, you find that the total mass of adding them all together is not the same as if you just measured this nucleus. For example, for carbon 12 with 6 protons and 6 neutrons, so 6 protons add 6 neutrons, you're going to have 6 times 1.673 times 10 to the minus 27, and you're going to add that to 6 times 1.675 times 10 to the minus 27, and you find that the mass of the combined nucleons is 20.09 times 10 to the minus 27 kilograms. But the mass of carbon 12 nucleus is equal to 19.9 times 10 to the minus 27 kilograms. Doesn't seem a lot, but it's missing, and that should not be the case. But it just does not make sense. It's like if I had a bag of billiard balls, and I took these billiard balls and I measured them all on scales, and I wrote down the masses of all these balls. I then put them in a bag, I measured the bag, and somehow some of that mass had fallen out the bag. It just disappeared. It makes no logical sense. However, remember, E equals mc squared. If you, what happens is this missing mass, we call it the mass deficit. once you have that stable combination of protons and nucleons, this less massive nucleus has a lower potential energy than the separate nucleons. So let's think what that means. So if you have, we've said previously that these nucleons are held together by the strong force that glue the nucleons together. So they've got the strong force working to hold the nucleus, to bind the nucleus together. If you wanted to separate the nucleus parts, if you want to pull this proton out of here, you need to do work to remove the nucleons, i.e. to overcome this force. Remember, work is force times distance. So we wanted to remove this proton to some distance over here. You'd have to do work against the strong force, just in the same way if you were going to lift a brick from the ground up to some height, you have to do work against gravity. This mass deficit is the work needed to pull the nucleus apart. When it's in this state, it's like that brick sitting on a bookcase. It's got gravitational potential energy. These nucleons have potential energy. When they're in this stable state, they're in this state of where there's this nuclear potential energy there, and because they're being held with the strong force, this mass deficit is what we call the binding energy. It's this potential energy that is locked within the nucleus. So this mass deficit is is what goes in to make the energy the binding energy. So the binding energy for any isotope of an element is calculated using E equals mc squared. So if we find the difference in the masses of all the different separate nucleons, and we take the actual mass of the nucleus away, that mass plugged into here gives us the binding energy for carbon 12. Now, this turns out to be a very, very important discovery in nuclear physics, because if we graph the binding energies of the different isotopes of the different atoms, we come across, put a different background on it so we can see it better. We come to this graph. This is the most important graph in nuclear physics. What it is, the binding energy per nuclear particle, per nucleon, and megaelectrons volts against the mass number A, so the number of nucleons in a nucleus. And so hydrogen down here, it's only got one nucleon, and so the binding energy for this is for the one nucleon is down here, and then it shoots up. This here is the energy yielded by nuclear fusion. What we find once we get to iron is the most stable and tightly bounded nucleus that there is, and then we see it dropping away, and as we get to these less stable isotopes, we find that this is where we get nuclear fission. Once we get these big nuclei which break apart and in nuclear fission to make smaller nuclei, the average mass of a product of nuclear fission, it has a mass number of 118. This means from an energy perspective, it is possible to combine. So here we've got, on this side of the graph, we've got nuclear fusion, and on this side, we've got nuclear fission. So up to here, it's possible to combine nuclei to get a bigger nucleus, but after this, you can't combine nuclei to get a bigger nucleus. From an energy perspective, nuclei are going to break apart to form smaller nuclei. This also shows us why, when we have nuclear fusion, if you were to have a big nucleus here, like uranium breaking apart and making smaller nuclei, there's going to be a difference in the energy released from this heavy nucleus to lighter nucleus. That there's an energy difference here, and that's the energy that would be released within that nuclear fusion reaction. The processes of nuclear fission are what are vitally important to life on Earth, because this release of energy when you have smaller nuclei coming together to make heavier nuclei, this is what is fueling the sun and therefore life on Earth. So let's look a wee bit more closely at nuclear fusion. Where is that layer? That is, there it is down there. So let's get another tab up. So we're going to look at nuclear fission. So fission is when you've got heavier nuclei breaking up to get lighter nuclei. Radiation carries energy. When we have, let's look at an example. Let's look at uranium. Uranium 236, and uranium's atomic number is 92, and that breaks down into barium 144, 56 plus 89 krypton, 36 plus 3 neutrons. Now again, if you add the mass of the mass of the uranium and the mass of its daughter constituents, you find there is missing masses, and that shouldn't happen. You should have conservation of mass. And what you find is that missing mass is in the form of energy. So let's say the mass of the uranium and then the mass of the daughter particles put this one down here, and the one neutron is 1.67439 times 10 to the minus 27. So this is the mass before, and the mass after is going to be 3.9166 times 10 to the minus 25 kilograms. That therefore means a mass difference of 2.97 times 10 to the minus 28 kilograms. Therefore, the energy released per atom is going to be, using E equals mc squared, plug this mass in here, and the speed of light squared, will be 2.675 times 10 to the minus 12 joules. That does not seem an awful lot of energy, but that is from one atom. You're going to have many, many atoms in your sample. 1 mole, remember 1 mole of a substance is equal to 6 times 10 to the 23 atoms. So you can quickly see a few moles is going to be, you're going to soon get an awful lot of energy. And once we were able to start harnessing this power, we were able to generate large quantities of energy and use them in nuclear power stations and obviously in nuclear weaponry. Now, the isotope 236 is very, very short-lived. And it's because it's such a short-lived isotope, you don't find it much in the Earth. So what we use instead is the slightly more stable uranium-235, and we bombard it with neutrons, and that then forms our 236 uranium, which then quickly will break down into its daughter particles. Oh, there's 3 of them. 3 neutrons. Now, these 3 neutrons are quite important. If you've got a sample of uranium-235 and you're bombarding it with this 1 neutron, you're very quickly going to end up with 3, which are then free to bombard more uranium, and you quickly will then, after 3 of these, bombarding 3 more of these, you're then going to have 9 reactions happening, and you end up very quickly having a chain reaction. And we call this nuclei fissioning, which keeps happening. Each one is going to be, the amount of energy released each time is going to grow and grow and grow and grow, and you can get an out of control reaction. That's what happens in a nuclear bomb, where you release this energy and you create this chain reaction very quickly to produce a huge amount of energy in a very short space of time, to devastating effects. If you're wanting to produce electricity, you do not want a chain reaction, because it would not be good, it would be devastating. So in nuclear power stations, you need to control your reaction to be able to generate electricity. So there's a number of different things that nuclear physicists will put in place to control this chain reaction. So the first thing is they'll have a moderator. So this controls the speed of the neutrons. If the neutrons are going too quickly, they won't actually be captured by the uranium nuclei. So they need to moderate the speed to increase the probability of a collision with and inclusion into the uranium nucleus. So it's not even just a collision. If it's going too quickly, it might collide, but it might be have so much energy it would just bounce off. So you need to have that optimum speed of the neutrons. But you also need control rods. These mop up excess neutrons, so they control the number of neutrons available, thus preventing an out of control chain reaction. And you also need a cooling system. Massive amounts of heat are generated, so water is used to transfer thermal energy to steam generators, and thus that's how the electricity is then generated in these steam generators. So it's this thermal energy that we want to utilize in the generation of electricity. There's other safety precautions put in place. Obviously, the nuclear reactor is encased in a well-designed reactor so that the nuclear energy is contained, that there's no loss of radioactive material from the reactor itself. So there's lots of different things that are put in place as well to make this as safe as possible. Nuclear fission is the opposite. As we've already said, nuclear fission is what we have in the sun, and it's what makes life on Earth possible. So, not fission, I've written fission, fusion. Let's just get rid of that. Fusion. So that's when we have two low mass nuclei coming together to form a more massive nuclei. So for example, two hydrogen atoms forming a helium atom. Now again, if you do accurate mass measurements before and after the fusion reaction, you find there's a similar mass deficit as we had with the fission reactions. The total mass of the resultants is greater than the total mass of the products. So if we have hydrogen 3, so this is an isotope of hydrogen, and we smash two of them together, we form helium 4 plus 2 neutrons. And this shows us, if you do all the maths, you have a mass deficit of 2.02 times 10 to the minus 29 kilograms, which is equivalent to, for E equals mc squared, 1.818 times 10 to the minus 12 joules. And again, that's one atom. When you scale that up to a big sample, you get a massive amount of energy released. You also, the other thing with this, with fusion, is you don't get the nasty waste products that you get with fission. So when you have the fission reaction, you're ending up with large quantities of radioactive nuclear waste. When you do nuclear fusion, you get helium and some neutrons. The products are safe. This means that nuclear fusion is an area of study in physics as a potential future fuel source, and they're near cracking it. As we're about to see that there's huge engineering problems that have to be overcome. So when we look at, for these two hydrogen atoms to collide, they need to have a very high initial kinetic energy. In order to force the atoms together. Now, in stars, the massive gravitational fields that exist in stars create those conditions that these will have sufficient energy in order for nuclear fusion to occur. But on Earth, recreating what's happening in a star is very, very difficult. Now, the kinetic energy of a particle is the same as its temperature. So the temperature of a particle is what gives it its kinetic energy. So for the temperature for fusion to take place, you're looking at temperatures of an order of 10 to the 7 Kelvin. Now at those temperatures, this strips the electrons. So you have a super hot plasma. If you have this in a reactor and you raise the temperature to 10 to the 7 Kelvin, you strip off the electrons, get this really, really hot plasma. The temperatures are so massive that they would melt or evaporate the material that the holding vessel was actually made of. So this is a huge problem, and it's been overcome by creating something like this. So you've got this vacuum vessel, this blue bit here. In here you've got the plasma that goes round and round, and we use a massive magnetic field, and this magnetic field can control and contain the plasma in this ring, and this plasma will rotate in this ring really quickly, and it will you'll be able to then generate electricity from this process. And you can get within the plasma here, you will have the atoms will be able to get to such a temperature, such a kinetic energy, that nuclear fusion can occur. And they are building these things. So here are a picture of one of these chambers actually being built. So this design was first come up with, the solution was come up with by the Russians in 1950, and it's called a toroidal chamber with magnetic coils. they are building one of these in the south of France, just like CERN. This is a hugely expensive thing to build, and there's needed international collaboration to fund and to overcome the engineering challenges of building it. The schedule is that they will have a functioning, working nuclear fusion generator by 2025, with the hope that very shortly afterward they'll have a commercial power plant. The one in France is known as ITER, so the International Thermonuclear Experimental Reactor. Now, to reach commercial viability, the power output, so the output needs to be 500 megawatts. But to achieve this, the power required to ignite and sustain the plasma is 50 megawatts, which is massive. So these are the constraints. But if they can solve the problems, get this working, this could be a solution to our energy requirements in the future, because it is clean. There is no nasty waste that is produced, and it can give limitless electricity and power to us if they can solve this problem.